dark matter, dark energy, these things we don't know how to define just yet. Can you just give us a quick intro on those two topics?
So you're asking for the 10-second description of how the universe entirely works.
This is NASA's Curious Universe. I'm Sophia Roberts. NASA is launching a new space telescope that will change the way we see the universe. It's called the Nancy Grace Roman Space Telescope. Roman will study some of the biggest mysteries out there. It will answer questions about how the universe has changed over time, what's driving the expansion, and the worlds that exist beyond our solar system. Roman has the unique ability to survey vast areas of space with incredible speed and detail. It will collect huge amounts of data, including more than 1 billion galaxies, and help discover thousands of planets orbiting distant stars. Roman will join other telescopes, including Hubble and Webb. It builds on NASA's technology and know-how and carries on NASA's legacy of light that has shaped our view of the cosmos over decades. I have been in the clean room watching this telescope come to life over the last few years. I have interviewed plenty of people who are testing it and constructing it, and I am personally so excited to see the universe through Roman's eyes. In this episode, we're going to dive deep into Roman with Julie McEnery. She's a senior project scientist. Hi, Julie.
Hello.
Let's start from the beginning. Roman has been years in the making. Talk to me about where the journey began.
In some senses, the journey for Roman began at the end of the last millennium. In the late 90s, we realized that the universe was behaving much more strangely than we imagined. And that instead of coasting out at a constant speed forever or slowing down, it in fact is accelerating. Huge, unexpected mystery. Many scientists wanted to figure out what can we do to take the next step to understand the fundamental nature of our universe.
I would like to know what, from all of you, what you think the next steps are. I mean, should we study more stars in the galactic bulge to find out more? What's the next step for the planet-finding quest?
That led to groups of scientists developing ideas for mission concepts. At the same time, another group of scientists were thinking, we would really like to have an observatory that can find planets around other stars using this fairly new technique called microlensing. And then finally, there were a third group of scientists who were interested in what if we could do really large surveys and just explore the fantastic astrophysics that you would have from surveying large regions of the sky with exquisite sensitivity? And that combined mission, the mission that does it all, was called WFIRST, and then later was renamed to the Nancy Grace Roman Space Telescope.
So it all starts with the science questions.
Of course.
And then you have to figure out how to do it.
That's half the fun. Yeah. It's exhilarating that we're making so much progress so fast. I'd forgotten how, as you get closer to launch, everything just keeps on coming at you, that it's test after test after test. And, we've passed all of the tests, but that's not to say there haven't been some little bumps on the way. I mean, we've identified things that we've needed to address, that we've needed to fix. So it's not like we're sitting back, like watching these tests all getting done and it's all like hunky-dory. It takes real work to make a cutting-edge observatory reach its full potential.
Did you always want to study space, even from childhood? How did you get into this field?
So I passionately care how the universe works. Not how the things in it work, but how the universe itself works. And so there are two directions that you can go with that. I mean, one place to fundamentally understand how the universe works is to look at the very small, the fundamental nature of particles and matter, the kinds of things that are studied by particle physicists. That's of extreme interest to me. And the other area is the study of the very big. What is the property of the universe we live in? How did it start? How has it evolved? Where is it going to go? What is the fundamental nature of the underlying physical laws that drive that? And through my career, I've touched on both of those things, the very small and the very large. With Roman, we focus on the very, very large, and we do an enormous amount of really cool astrophysics as part of that journey.
And what are you personally hoping to study or have revealed over the course of the mission?
So I'm keeping an open mind. I think when you build an observatory that has profoundly new capabilities, the most exciting science is going to be the thing that you didn't expect. So you want to approach what you're going to do with the observatory and how you're going to use it with something of an open mind so that we can pivot to following the surprises, following the things that are most that are most impactful. With Roman, we're discovery space on steroids. Because we do large surveys, we're not picking a galaxy and going to study that galaxy. We're not picking a star to go and look at that star. We're mapping out large regions of the sky with extraordinary sensitivity. And we're going to find all the things that are there. So we're going to study the things that we know about, and we're going to find the things we didn't even know to look for.
That I love. But are there big questions that maybe keep you up at night?
I mentioned towards the beginning of our conversation that one of the motivations for Roman was the discovery that our universe is not just expanding, but that expansion is accelerating. Now, that's crazy. I mean, it's like if you were to throw a ball in the air and instead of the ball coming back down, it just keeps shooting away. So that itself is surprising. But, you know, cosmologists are clever people. There is a model, lambda CDM, where lambda is a cosmological constant. It describes the property of the universe that pushes the universe to accelerate. And this model is spectacular. It's really good at taking all the things we measure in the early universe and accurately predicting all the things that we are measuring around the current time in the universe that surrounds us today. But in recent years, a couple of cracks have appeared. So all of that is pointing to there's something really fundamental that we don't understand about the nature of our universe itself. And Roman is purpose-built to address and provide the data that we need to address these questions. So I'm very, very excited that we happen to have the right observatory to address what I think is one of the grand challenge scientific question of our time.
Those are one of wonderful goals that Roman has, because one of its major jobs is to investigate dark matter, dark energy, these things we don't know how to define just yet. Can you just give us a quick intro on those two topics?
Sure. So you're asking for the 10-second description of how the universe entirely works. If you make a pie chart of what makes up the content of the universe, just over 20% is this quantity dark matter. It's actual matter. You can see where it exists because of its gravitational impact on objects that we can see, but otherwise seems invisible. Dark energy makes up about 75%, and dark energy describes the phenomenon of space-time that drives the acceleration of the universe. And then you've got like 4 to 5% of the universe that is ordinary matter, but that's stars, planets, us, everything else in the galaxy. So the things that we actually observe is a small fraction of what the universe itself actually is.
So if we can't see dark matter, for example, how are we going to study it with a telescope?
If you take our own galaxy, there are streams of stars that are moving across the galaxy. And as those stars are moving, if they pass by a little clump of dark matter, the gravitational force of that clump of dark matter is going to perturb this stream of moving stars. And we can see that, and we can measure it. We can measure how much dark matter is in a galaxy by looking at how fast the stars on the outside of that galaxy are moving. One of the things that we're planning to do with Roman is to study dark matter on sort of large scales of the universe. And what we do is we measure millions and millions of galaxies, hundreds of millions of galaxies. And as the light from those galaxies passes through the universe to get to us, as it passes through matter, which, as I've just said, is mostly dark matter, the light gets bent a little bit. and it slightly changes the shape that the galaxy appears to us. Those galaxies are acting like lenses. So we will be measuring this from those millions of galaxies and using that to create a 3D map of the dark matter in our universe. And the distribution of that dark matter will tell us a lot about the nature of the dark matter itself.
How do you hope to learn about dark energy?
So dark energy drives the expansion of the universe. We have several different ways that we can measure the expansion history. One of them is to look for what's called a type 1a supernova. And that explosion always happens at the same mass. So it has the same brightness, or can be made to be the same brightness. So they're like a standard candle. So if we know how bright something is, and we know how bright it appears to be, we can figure out how far away it is. And that gives us a way to measure the expansion rate of the universe. So when we measure the expansion history of the universe, when we measure the rate of acceleration, when we measure how that acceleration is changing with time, that is the information that we need to better understand the nature of dark energy itself.
And we can only do that with something that has a huge view, right?
We can best do that with something that has a huge view, because when you're measuring the property of a large chunk of the sky, you can be reasonably confident you're understanding how the universe itself is behaving rather than the vagaries of a particular small group of galaxies in one particular spot.
Roman will be studying exoplanets, and these are the planets that are orbiting other stars. How will Roman teach us about more exoplanets?
In short, by finding an awful lot of them. We expect with Roman to find somewhere between 60,000 and 200,000 exoplanets, which is a lot. The way that we do this is we're going to be pointing our telescope close to the center of our galaxy, where there's lots and lots of stars. We will be really precisely measuring the brightness of a few 100 million stars every 12.5 minutes for months. And when we look at that data, we can use that data to find new planets. And there are two ways we can do this. The first is the more traditional way. If you have a planet that is close to its companion star, and if that planet is pretty big, when the planet goes in front of the star, the apparent brightness of the star dims. That's what's known as the transit technique. And that's where most of the exoplanets that we know today have how they've been found. The second technique is to use microlensing. And microlensing, it's actually really cool. You have a star that you're looking at, and then you have another star somewhere between us and the background star. And as we move around, as we being our solar system moves around the galaxy, every now and again, there is a chance alignment between a background star and a foreground star. And when that happens, the gravitational potential from the foreground star acts as a lens for the light from the background star. So what you see is the brightness of the star increasing and then decreasing as the foreground star passes in front of the background star. If the foreground star has a planet around it, what you see is an increase and a decrease caused by the star, but then there's a little blip that is a smaller, shorter increase caused by the gravitational potential of the planet itself. And the reason this is so important is this allows us to find planets that are further away from the host star. And it's opening our eyes to the distribution of planets all the way from close to the star right out to the equivalent to the outer solar system and beyond. So with Roman, we're going to have a complete picture of how many stars, how many planets are around stars, at what distances, what masses are those stars. And we can use that to really hone our ideas and models and understanding of how planetary systems, including our own, form in the first place.
And then let's talk about how this instrument that's going to be doing this, the coronagraph, is setting us up for future missions.
The previous two techniques, we find the planets by their impact on the brightness of a star. But what if you want to measure the planet directly? Then the brightness of the star is the problem, right? You need to figure out a way of blocking the brightness of the star so that you're not dazzled and you can see the planet sitting next to it. So what we do with the coronagraph is we put some sort of a mask in front of the bright star, And if we just put a circle on it, it wouldn't really work, because I think of it as doing magic with physics. Light behaves like a wave. So you have a property known as diffraction that means that even if you fully blocked out the star, some light will still get past. So what we do is we have a sequence of masks that combine the light together in a way that causes destructive interference and turns it off. And when that happens, then you're able to see the really faint planets next to it. So what we're going to be able to do with Roman is the equivalent of seeing a firefly next to a lighthouse in Los Angeles, observed from DC. And that isn't quite enough to get you to seeing an Earth-like planet around a sun-like star, because that would be trying to find a bioluminescent algae and not just a firefly. But it's still really hard. So to do this, we have to have mirrors that deform so that we can have exactly the right alignment and optical prescription to get this zeroing working. And what Roman is going to do is to test these deformable mirrors for coronography in space for the first time. We're going to test extraordinarily sensitive, low noise detectors. And we're going to develop and test and use state-of-the-art processing algorithms to go from a bright star to a direct measurement of a planet.
What sets Roman apart from other telescopes that NASA has?
Roman is set apart from other telescopes by having huge numbers of things. We are going to have several billion galaxies. We're going to see tens of billions of stars. We're going to see tens of thousands of planets around other stars. Whew. And so it's just sheer numbers of things. And it's not, I mean, just seeing sheer numbers of things, yeah, we're seeing more things. That by itself is not interesting. It's what you can do because you have numbers of things. I mean, we are going to be able to tell you what kind of planets form around what kind of stars and in different regions of the galaxy. And that will give us a completely new handle on understanding how planetary systems form. You know, we can survey the sky extremely quickly and efficiently. And we actually survey the sky with the sensitivity and performance of Hubble, but 1,000 times faster.
Can you tell me what happens after launch? What is the science team up to? What is it like choosing the first images, or what are the first things that you hope that the telescope will be up to?
So the first few months of the mission, we are focusing on understanding the observatory. And that's a lot less boring than it sounds. So Roman's observing program, most of our observations are on 3 really large, completely phenomenal surveys. The beginning part of the mission is going to be to collect data that will allow us to determine whether what we plan to do with those surveys is actually going to work. So we're going to collect data on a deep field. And the Roman deep field will have the same depth as the Hubble deep field, but it's going to be over 1,500 times larger. Completely blow your socks off. There's going to be enormous science and potential there.
So I guess you can't give us a hint of what the first images might be.
I mean, we know where the deep fields are. We're going to go and look there. It's Roman is less the big reveal because what we plan to do with our observations has been extensively discussed across the community. However, obviously, we may spend a little time choosing to go to places on the sky that we know look really cool, so that we can have a debut to the world that says, here we are, here's some cool pictures. It's the teeny tiniest taste of what's to come.
And it's going to be tough to even show them because they're going to be so huge.
So you could think of it as, if I take one Roman field of view, how many 4K TVs is needed to display that image at full resolution? And the answer is, it takes 36. I think, well, that's fine. But Roman doesn't observe in a mode with just one field of view. We map out a huge region of the sky. So you could ask the question, okay, well, how many 4K TVs would I need to fully display our largest survey? And that's over 500,000 4K TVs. And, most of us, myself included, don't have a picture of what 500,000 4K TVs are like. It's the equivalent of covering 45 city blocks. You could think about Mount Rushmore, but Mount Rushmore's too small. You would need to fully cover El Capitan with 4K TVs to fully display Roman's largest survey. I don't think we should do that, but, it gives you a sense of how amazing this survey is going to be.
Just trying to think of how we even view any of that.
Well, what you'd have to do is you'd have to give people a telescope so that they could view the images that were on the 4K TVs that were on El Capitan.
Ha! Okay, looking out into 5 years' time, what are you hoping that Roman will have done, contributed?
In 5 years' time, we will have definitively addressed whether the model I talked about earlier, Lambda CDM, our standard model of the universe, is broken. And we will have provided the data to tell us, or at least put us on the path for knowing what's correct. We'll have increased the number of known planets by a factor of 40. We will have measured more supernovae to greater distances than has ever been done before. And we'll combine all of that into, the data to understand the universe. We'll find surprises, the things that go bump in the night. We'll find the things that go bump in the night that we know about. Afterglows from gamma ray bursts, which are stars that are exploding and turning into black holes. We'll find tidal disruption events, which is where a star is swept into a supermassive black hole at the center of the galaxy. And then we're also going to find surprises. We're going to find the things we didn't know to look for. We're going to detect several billion galaxies. So we're going to find the unusual galaxies. We're going to find the unusual galaxies that allow us to understand how galaxies themselves form and evolve from the earliest time to now.
Do you hope that it changes our understanding of physics?
I don't think I hope that. I think I know that.
On to Nancy herself.
Okay.
Did you know her?
I mean, I wouldn't say I knew her very well, but I certainly encountered her several times. She was in the audience twice when I gave a presentation, and sometimes in pretty small environments, and she was wonderful. She had a background in science and engineering and technical management that she could ask questions about all of what we're doing. She was extremely sharp, extremely insightful, and very intolerant of occasionally people assuming she might be less sharp than she actually was. I didn't ever make that mistake, but I've seen it happen, and she is quite good at correcting that kind of misconception.
Good for her. What does it mean to you that this telescope that you are leading is named after her?
I think it's fantastic to be associated with an observatory that is named after a person you admire. Right? I'm proud to work on a observatory that is named after Nancy Grace Roman. And I think that's really nice. I think it's really important. I think we can strive to try and do things in the way that she would have liked to have seen them done. I think she might be proud about what we're doing too.
We are so close to launch. So many things have happened leading up to now. You're sort of helming this whole thing, but what is it like for you to be so close to the science that you've been reaching for honestly, the last decade, I guess?
It's somewhere between exhilarating and terrifying. I'm incredibly excited at being this close to sort of realizing the dream of getting these observations. But I also really feel the pressure and responsibility of all of the other scientists who have been along with us on this journey, who have been working on Roman, developing the ideas, developing the theories that we're going to test, the algorithms that we're going to use to process the data. And there's a chunk of me that is, I really want to make sure that I don't mess things up, that I can't by myself make things successful, but I sometimes worry I have a potential to be able to single-handedly mess it all up, and I don't want to do that.
It's a team effort.
Yes. In the moments where I have time to take a deep breath, I feel proud, but mostly I'm just running to keep up. I mean, and this is very exciting, right? This close to launch, it's exhilarating. Everything's coming at us really fast, and this is going to continue. I mean, we're going to get to launch. We're going to launch, and then the fun really begins. So, when I might feel proud is probably about 6 months from now, when we can take a big deep breath and we've built it, we've launched it. We've made it work. We've started to do science. We're going.
Julie is the senior project scientist for NASA's Nancy Grace Roman Space Telescope. And thank you very much for joining us here today.
Thank you. It was a pleasure.
Go Roman. The Nancy Grace Roman Space Telescope will launch no earlier than August 30th. I hope you're as excited as we are. We'll be there in Florida to cover the launch, and we'll be back in your podcast feed soon with more about Roman.